Hello everyone, welcome back our class. Let's continuously study chapter 4, convertibility of energy, exergy analysis. Section 4, exergy analysis of system. We know some systems certainly include some exergy. When a system passes from a given state to that state, it can do some work. If the process is reversible, it completes the work certainly to be maximum. The exergy of a thermal system is the maximum theoretical work obtainable from the system as the system passes from a given state to that state. If the maximum theoretical work certainly just is the exergy. Just to say, when system from this state gradually change into the environment state, can do some work for the user. If the process is reversible, certainly the system can complete the work is maximum. The first one we discuss the exergy of a closed system. A system delivers the maximum possible work as it undergoes a reversible process from the initial state to the state of its environment. That's the dead state. In this process, can do some work. This work is exergy. If the system, the parameters with V, U, S, the environment, the parameters is T0, P0 respectively. The energy equation is delta QRE equals dU plus delta WU maximum. This equation from the first law. We know P0 dV is an unavailable work to drive the environment. No use for the people, for user, so it is not exergy. Considering system and environment together, when the system absorbs the heat, certainly the environment released the heat. So delta QRE certainly equals minus delta Q surroundings. One give, one obtained. In reversible processes, the total entropy change of system and environment is zero, because system and environment together is an isolated system. So the total entropy change is zero. ds plus ds surroundings equals zero. Obtained ds is minus ds surroundings. So the entropy change of environment is ds surroundings equals delta Q surroundings over T0. Because environment, the entropy change is easy to be calculated because environment has the constant temperature T0. We know delta Q surroundings is minus delta QRE, so ds surroundings equals minus delta QRE over T0. We calculate the entropy change of environment. Therefore, we can obtain delta QRE equals T0 ds. In this case, we can calculate the heat transfer, heat energy relation with entropy change. From the energy balance equation, we easily obtained in reversible process delta QRE. System obtained the thermal energy equals du plus delta W maximum together du plus delta W maximum. We know delta W maximum certainly equals P0 dV and delta WU maximum. Delta WU maximum is useful work, the maximum useful work, because delta W maximum is not change usable. All of it is not useful work. Only part of it is useful work. P0 dV is drive the environment to the work, is not useful. So this equation comes from energy balance. Finally, the maximum work, delta WU maximum useful maximum work equals minus du minus P0 dV plus T0 ds. We obtain this equation. Very important, very useful. Okay, integrating from the initial state to environment state, we obtained the useful work, the maximum work. WU maximum is the largest, the useful work, equals U plus P0V minus T0S minus U0 plus P0V0 minus T0S0. Two terms minus. That's the exergy of a closed system in T0, P0 environment. It is also the maximum available work. So it is the exergy of a closed system. So the exergy EX is U plus P0V minus T0S minus U0 P0 V0 minus T0 S0 is two terms minus. Sometimes we order D function equals U plus P0 V minus T0 S. Sometimes we can call it a function. Then the exergy we can use D function to calculate is Ex equals D minus D0. D0 means in environment state, the D function. Sometimes we can use this equation to calculate the exergy. Sometimes we can call it D is available function of a closed system. If the system changes from state 1 to state 2, just from state 1 to state 2 is not to the environmental state, then the completed the maximum work just is the exergy difference. So WU maximum equals EXE minus EX2. And last page we discussed the exergy of a closed system. Here we will calculate the exergy of an open system. Under steady state flow conditions in environment P0, T0, we know the system parameters P, T, H, S. Environment, the parameters may be P0, T0, H0, S0. Sometimes we need to consider the kinetic energy and the potential energy. So kinetic energy EXKE, potential energy EX potential, we can calculate. So the energy balance equation for open system, we obtained delta QRE equals DH, just the enthalpy change, plus delta WU maximum therefore WU maximum, useful work, the maximum. And the kinetic energy change, potential energy change, we obtained this equation just from the first law. Okay. Similar as the closed system, because the system obtained the thermal energy just as the environment released the thermal energy, so we obtained delta QRE equals T0 ds, just from the similar as the closed system. From that page, we obtained this equation. So for open system, delta WU maximum equals minus dH minus T0 ds minus Ex kinetic energy minus Ex potential energy. Sometimes, many places, we can ignore the kinetic and potential energy because the change maybe is not so big. If the kinetic energy and potential energy can be ignored, integrate this equation, the open system, the useful work equation, we can do some integrate from initial state to environment state. We obtained WU maximum equals H minus T0S minus H0 minus T0S0. We obtained this equation. It's very, very common, very important equation. Just is H minus H0 minus T0 times S minus S0. Finally, just equals delta H minus T0 delta S. This equation is very important for open system. We use Ex express the exergy, so Ex just is H minus T0S minus H0 minus T0S0 for open system. If the system only undergoes state 1 to state 2, the maximum work is WU maximum equals Ex1 minus Ex2. For unit mass, sometimes for convenience, we only discuss unit mass. So unit mass Ex, small ex, equals small h minus T0 small s minus H0 minus T0S0. This equation only for unit mass.